Hi, it's Dave. Elon Musk has shared that Tesla is building a supercomputer called Dojo, and that Dojo will be an important part of how Tesla trains and improves their full self-driving features. But have you ever wondered what exactly this Dojo supercomputer is? And why does Tesla need to build it themselves rather than use what's already out there? In this video, we're going to dive into this with machine learning expert James Douma. What follows is an excerpt from a conversation I had with James Douma. He's a software engineer and investor with a deep passion for machine learning. He's been following self-driving efforts since the early 2000s and has put almost 80,000 miles on autopilot on the 2 Teslas that he's owned. I first learned of James when he posted some fascinating details of Tesla's early neural nets a few years ago on teslamotorsclub.com. And as Tesla's full self-driving beta has started to roll out, I've been wanting to get a clear sense of what's going on under the cover. How fast is Tesla's full self-driving features going to improve? Why did Tesla have to do a rewrite? And what is the Dojo supercomputer? If you're interested in watching the full interview, which is 3 hours long, I'll post that link in the video description. Also, later this week, I'll be posting another excerpt from an earlier conversation I had with James Douma about the possibility of a Tesla robot in the future. I want to ask your take on this Dojo training system that Tesla is developing. Elon has mentioned it. People have gotten excited about it, but I don't know if many people really know what this is. What does it do? Can you explain, what is, Tesla's Dojo system? Why did they make it, and how will this help Tesla's full self-driving, autonomous efforts going forward?
So one thing about deep learning neural networks is that they scale really well with power and data, with the compute power and data. That is, one simple way to make any system better, to just improve its accuracy, is just, make the neural network bigger and feed it more data and train it for longer, right? A lot of systems don't scale with just simply by throwing more compute power at the problem, right? Classical coding systems don't. Microsoft Windows doesn't get any better if Microsoft uses twice as many computers to write it, right? And most of the code in the world is like that. But there's economic limits to how big a system you can put in the car and how big a system that you can train on data. So you want to be able to economically train these systems. That means you need to do the most computation for a reasonable amount of money that you can get away with. So hardware today in the deep learning world is it's in kind of an interesting place. Deep learning is a new enough tech that when it first came into the world, there wasn't any hardware built that was specialized at doing what it does. And in fact, the best hardware actually wasn't a very good match for what deep learning really needs to do. And that's why a company like Tesla can basically make their full self-driving chip, right? They take a relatively small team of guys, they give them 6 months or 2 years or something like that. They're not even working on the latest process node. And yet they can come out with a chip which is dramatically better than any commercial solution that you could put in the car. It's much lower power. It's going to be higher reliability because it's a better fit for this thing. It's dramatically higher computational capability. And this is because it's architected for doing exactly what neural networks need to do, right? So similarly, the training hardware has similar kinds of limitations in the world today. You can go out and you can buy tons of CPUs and tons of GPUs, and you can build an HPC, high performance computing cluster, and network all this stuff together, and you can do training, and it costs a certain amount. Right. This basically comes down to how much money do you want to spend training your neural network, right? So if Tesla wants to keep making the system better, they want to keep increasing the size of the network. They want to keep adding more data, and that means they need to train bigger and bigger and bigger networks. They have another limitation also, which is that up to now, a very substantial fraction of the data that they use for training the network is hand labeled. So they've got this army of people this is not like Mechanical Turk people, right? This is people that have been trained to do labeling, to use internal tools at Tesla, and they go through this data and they evaluate it. They do essentially markup on this data to provide training targets for certain parts of the neural network that are heavily dependent on this right now. So the amount of data that they can feed into the training system is limited by the number of people that they have to do this. And people are expensive. You could have 5,000 or 500 of these people, right? But having 50,000, that starts to get really expensive. So if you want to scale up 10x or 100x, you need to find a way to leverage them. And one of the things, there is a way to leverage labeling, which is this technique that they've described, where essentially let's use structure from motion, or let's use some mature geometrically based computational techniques to take a whole bunch of data and video from like all the cameras in the car at the same time, and let's use it to construct a 3D scene. Let's have the human labelers label that scene, and then you can push all that data back to the original frames. So this will increase the productivity of labelers like 100 times, maybe 1,000 times. I think those are the numbers that have been mentioned.
Like,
and I think that's realistic.
Like the 3D kind of structure through motion, that's what Andrei Karpathy was showing at Autonomy Day, right? Basically like kind of this 3D modeling. And I think in our last conversation, you were saying like to do that on the car side is going to be just intensive, not really that practical. But to do that, let's say on Dojo side is going to be, much easier. But also it's going to be where it needs to be, meaning they need that kind of structure through motion or 3D modeling in order to supercharge their labeling, right? So if I can paraphrase, you're saying like, hey, a label can go through that 3D scene, mark, car, mark cat, mark person, big truck, whatever. And then now that 3D modeling scene is actually comprised of thousands of frames, let's say, that made that up. But once they label it once, all of those labels will go back to the individual frames as labeling. And so it basically leverages their human labeling efforts but immensely, right?
So the thing about using, it's called SLAM, structure from motion. And it's not the only technique. There are other techniques too. But they're techniques that don't fundamentally rely on neural networks. They basically take a bunch of frames and they use pretty straightforward geometric processing, which is, I don't know if mature, it's probably not good to say that it's mature, but it's geometrically based. So you don't have to like train a neural network to do it. You can train neural networks to help, and probably Tesla and other companies will start using neural networks to speed up SLAM. But right now, SLAM is very computationally intensive. So you get this stream of data from a car. A car drives through a scene, and you have all the data from all the cameras and all the other sensors in the car. And you want to build this scene that a labeler is going to label. Well, some computer is going to go crank on that for a long time. And then they're going to present the scene to a human. So now you've got two limitations. You've got how fast can my computer crank out these scenes, in addition to how fast my people can label them. These are both moving targets, right? Because the tools are going to get better and the computers are going to get faster. But one thing that Tesla can do now, or that they will be able to do with Dojo, and they're probably already doing this with, Amazon cluster stuff, or maybe they have a data center composed of, NVIDIA boxes or something. I mean, they've got some kind of infrastructure that they're using now. So they can do this to some extent. And to the extent that they do it, it leverages their labelers. So leveraging your labelers, being able to train bigger networks with more data on the back end, these are all things that are very computationally intensive, right? And so looking out, over the arc, because we're not done with this now, right? This is, hardware 4 is going to come out. There will be a hardware 5 and a hardware 6. The networks are going to get bigger and bigger. And 10 years from now, this technology is going to be dramatically advanced from where it is now. We're not going to get to robotaxis and it's done, because robotaxis are going to get better and better. If you look along that arc, it's very important to bring the cost of computation all along that arc down as low as you can get it. And right now, computation is a lot more expensive than it needs to be, because most of the computation is not done on silicon, which is specialized at doing neural networks. So Tesla has a neural network problem that they want to solve. It's all about neural networks. So, they could spend, $50 million to build a machine to build their own machine that has a certain performance, or they could spend $50 million and buy a bunch of NVIDIA boxes, or buy some boxes from Intel, or rent time from AWS and get less of that. So my read on Dojo is it's Tesla making an investment in infrastructure so that 2 years down the road, 5 years down the road, they're getting the most computation at the most economical price. And they also control their own destiny. I mean, one of the problems that you have with relying on cloud providers, which is a really attractive alternate way to go, is that somebody else owns a critical piece of your infrastructure. It's like leasing your car factory. You don't want to do that. You want to own your car factory. You don't want to lease it from GM because GM is maybe a competitor in certain respects. Mm-hmm. And I think it's exactly the right thing to do. I've been arguing like in the circles and the deep learning circles for some time that we needed to get off of GPUs and we need to get onto accelerators as fast as we could. I was super happy when I saw Google go to TPUs because that was the existence proof that there's a lot of low-hanging fruit in making custom silicon to do the neural networks. And Google's gone to, the second and third generation of that kind of stuff. You see some startups making this stuff, but there's no commercially available part that you can buy today, which is really deep learning specialized. And so, that's why Tesla had to make their own silicon for their car because nobody else was doing it. And it's strange, but it seems like the economic incentives aren't really there to do it. Like the people who are in the best position to actually bring, these custom neural networking chips into the world, they're actually disincentivized from doing it because it would compete with other businesses that they have that are already making a ton of money in this space, right? So Google's making their own silicon. Amazon has started making their own silicon. Apple makes their own silicon. Like a big chunk of the silicon that goes in Apple's phones now is a neural network processor that they use for adding value to a lot of things that the phone does and that they can't buy from anybody else because nobody's making it. So if Tesla wants an HPC infrastructure for training these big neural networks, I think they looked at the world and they made the kind of the same decision SpaceX did. We'd be happy to buy it from somebody else, but nobody else is making it, so we're going to do the development ourselves. Mm-hmm. That's what I think Dojo is.
Got it. So you were mentioning in our last chat that this custom silicon for neural networks it's not the same chip as hardware 3 inside the cars, right? Or hardware 4. No. So this is customized and made for basically data center type of big applications, like pooled computing together, right? So how long do you think that this has been, like, do they have the chips, like these custom chips, running right now? Are they just slowly scaling this, or do you think it's like what point of the development process, and scaling process do you think they're at right now with Dojo?
So my read of Dojo is it's taking longer than they wanted it to take. And I think they probably got silicon getting first silicon, essentially doing an architecture, getting your first silicon back and whatnot, getting it running is that's a necessary first step to getting this stuff going. But designing an HPC cluster is a whole lot of really specialized technology on top of that is not traditionally like Tesla's strength, right? They're having to like grow a team that can do this, and those people are going to have to get up to speed, just like they had to grow a silicon team to make the silicon, right? And HPC infrastructure involves a lot of very specialized networking, all of these thermal issues that Elon has alluded to. That's a really big deal for HPC structures, and there's a lot of specialized tech and knowledge that goes into that. And I think Tesla's having to get up that learning curve, and it's going to take a while before they're able to deploy this at the kind of scale that's meaningful to their development efforts for FSD, right? Like having 100 of these things running in a back room someplace is not enough. They're going to need 1,000 or 10,000 of them. And you don't want to do that until you've put the effort into designing the thermal solutions, the power solutions, the network solutions that are needed to support this stuff. Mm-hmm. And that's just going to take time. And I think that's probably the long pole for them right now. It's not the silicon. I would guess they already had their first generation silicon on this stuff out.
Mm-hmm. Got it. I want to talk about labeling because I think most people don't really grasp like labeling, what it does. And I'm sure we can go on for like a couple of hours on, what labeling is and the importance. But rather than that, I want to maybe just like focus on, maybe I can share a bit of my understanding of labeling, and then you can kind of poke some holes or try to help me understand it maybe a little bit deeper or clearer. So my understanding of labeling is you've got this neural net, and I think we'll isolate it to Tesla's perception system, so how it gathers the images and perceives the world. And so these images are coming in, and I guess with this new rewrite, we have a fusion, the camera fusion, so you have maybe it's decided what the truth is in terms of what's happening, and as it comes in, it's going through a neural network of different nodes, and it comes out with an output of deciding what's in that perceived world, like what cars are there, what kind of cars, um, and what kind of people, just all of the different, buildings, etc. But the extent that this neural network can be accurate, can have accurate results, all depends on the the labeling. Meaning, in and of itself, the neural network can't really find out anything about. It could maybe parse the different, like, colors and textures and edges and shapes and all this stuff of all the objects, but it's not going to tell you that this is a cat or this is a person or this is a thing. That is all dependent on the labeling that's put into the system, which basically is the training of the neural net. So you're showing, the neural net a picture of a person, and you show a picture of a person or different types of people like a billion times, and the neural net's going to pick up on all the nuances, and it's going to learn what that person looks like, what a person looks like in different situations. And it's going to become more accurate over time, the more labeling or the more, training you're doing to that neural net. And so applying this to Tesla's case, I think like Tesla has trained their neural net with all this labeling, showing their neural net and this training of what is what, right, over time. And it's gotten to the point where it's decently accurate and the big things. But there's this whole field where there's a lot of cases where it's just ambiguous. It's like, is that really a car under the bridge or this lighting situation? It's just some ambiguity in terms of perception. And the neural net doesn't have enough training or enough data or enough examples shown to them and labeled where it can accurately discern what exactly that is. But to the extent that Tesla over time can increase the training and labeling of what, for example, that unique ambiguous situation is, and not just one time, but let's say they have thousands and thousands of examples from user interventions, etc., where they're able to pull those images, and the neural net wasn't really sure what that was, but through, let's say, human labeling, you label 1,000 of those similar situations. Now the neural net is getting better. It's saying, oh, now I know that situation because I've been trained, in what type of situation that is or what that is called, etc. And so the big challenge for Tesla's improvement of autonomous driving going forward is it needs to teach the neural net more and more, especially these edge cases and the March of Nines, these extremely kind of difficult, ambiguous cases. And the way they can do that is they take the data, especially let's say intervention data or situations where they know that the neural net hasn't really operated optimally, and they can take that and then try to label the situation better so that the neural net can get better over time. But the challenge is, I guess, if you only have 50 labelers or something, or 100, you're not going to be able to leverage the massive amount of growing data and growing, amounts of training that you could do it if you have more unlimited or scalable labeling. And so what Dojo is able to do is it's able to provide a way where labelers can supercharge their labeling, not just individual frames, but now structure through motion 3D models. So their labels can now go through and train the system even faster over time, thus increasing the speed of improvement for autonomous driving. So in that picture of my understanding of labeling, how it applies to, let's say, full self-driving, like, what am I missing something, or is that the gist of it, or what else can you add to kind of that understanding?
That's everything you said is basically right on. So neural networks, there's different ways of training neural networks. Actually, there's a whole zoo of ways now. But there's the most fundamental way is a neural network. It's a transfer function. It basically takes an input and it predicts an output, right? In the case of Tesla's networks, they actually generate thousands of outputs. They have many thousands of different things that they predict from every frame that comes in, or every set of frames that comes in from the cameras. They predict, where can I drive? Like, where can I safely drive? Where can I absolutely not drive because it's a cliff or it's a wall? Where are the lines on the pavement? Where is the crosswalk? Where are the signs? Where are the traffic lights? Which traffic light is appropriate to my lane? From here going forward, what is the smoothest path through the available space? And thousands of other things beyond that. Like there's these, they have these cuboids, right? Like every single object in the environment, which matters at all to the car, it draws a little three-dimensional box around it to figure out what the boundaries are. And those boundaries define a box that you don't want to enter, right? So like, a stop sign has a cuboid because you don't want to hit a stop sign, but then an animal on the road has a little cuboid around it, and all the cars have cuboids, right? They have like everything that's a curb, they label all that kind of stuff too. So the simplest way, and Andrej Karpathy has made statements along the lines of, yeah, we know there are all these other ways to do training, but this simple supervised training, it's the thing that we know works, and we know how it works, and we know how to make it work well. And so that's what we're putting almost all our effort into. They have things that they don't need labeling for. And like my favorite example of that is cut-in, because Karpathy gave a bunch of examples at Autonomy Day about exactly how they developed cut-in. The cut-in predictor is basically, if I'm driving in my lane, it predicts if a car in an adjacent lane is going to pull in front of you, right? Because you have to take action. And that was a big weak point that AP had until they got the cut-in detector. It was delightful to watch it develop over time and to hear from Karpathy how that worked, especially because it actually didn't require very much labeling, which is in contrast to most of the rest of the stuff they do. So when they started doing it, the car would take pictures, and a picture would sit in front of a labeler, and a labeler, they'd have this photo on the screen, and they're like, this is the center divider line, this is the, they would mark every single thing in maybe 100 different categories that was in the frame, and you would try to get the boxes around everything really accurately. Then what the neural network would do is it would have a lot of these examples, millions of them. Like, it's incredibly labor intensive to have a group of people go through all of this data and label it. And the neural network's job is it gets an image, and it has to tell you all these things about it. And it has to give you the same answer that the human labeler did, right? And you give it a different image, and it tries to do this. Essentially, with a neural network, every time it's wrong, and it's always wrong, it'll never be exactly right. It'll always be off a little bit. You can take that error and you can look at everything that contributed to that error in the weights in the neural network, and you can tweak them just a little bit in the direction of correctness. And it turns out if you have enough examples and you do this enough, the neural network will get really, really good at giving you the same answers the human being did, right? So when they were just in the camera, when they were only using camera networks, which, the camera networks, incidentally, the term I'm using, there's a big neural network attached to each camera, right? That processes directly it gets the frames from the camera, and then it does a bunch of processing, and it generates a few hundreds of different pieces of data that come out. And some of those pieces of data include, these are the lane lines I see, and this is where they are. And some of the pieces of data are like, these are the vehicles and pedestrians and objects of interest, and these are the cuboids around them. This is the volume of space they occupy. It predicts all that stuff for all of those things. So, at one point, they had a piece of software that took all these pieces of data from all these cameras, and then it would decide what the situation is based on that. And over time, what they do is more and more of that back-end processing is handled by other neural networks that train even higher level stuff. But the bulk of the data and the most important stuff is the stuff that comes from the cameras, and that's very labor intensive to label. This is what's called supervised training. Supervised training is where you have a whole bunch of examples, and you're going to give them to the neural network, and its job is to produce the answer that you know is the right answer, given the input that you know is a particular input. And so they take all this data from the real world. So an important part of labeling, and a thing that's not well understood about Tesla's network, or maybe it's well understood, maybe it's not well appreciated. There's frequently this kind of misperception that all the Teslas are out there just recording all this data and uploading all this bulk data. In other words, that the Tesla fleet functions as a video recording device that bulk produces all of this data that just then gets labeled and curated and goes in the system. And that's actually not what it does. It does something which is much more useful than that, which is, once you have this basic system working, right? So say you've built your network and you've got all your labeled examples and you run a bunch of stuff, the developers, they will start seeing patterns in the mistakes that get made. Like a good example is, you're coming up on a bridge and it breaks because it thinks it sees a wall because of a shadow or something like that. And the way you fix that with supervised training is you look at places where it made mistakes. You take those examples, you have a human label them, so with the correct label, and then you train the network on those. And what happens is the answers the network gives you shift away from the erroneous ones and they shift towards the accurate ones, right? But in order to be able to quickly grab a lot of examples of just the thing that you're having problems with, what you want in the real world is you'd like to have a fleet of 1 million cars out there where you can say, send me examples of this. You send them a request. I want this. And they take them and send them to you. And that's what Tesla's got. They're not absorbing. The fleet is not a data collection thing. It's a look at the world and find examples of this particular thing that I'm asking you for. Because what Tesla needs is not lots of data. What they need is a very specific data. If I was to say, Waymo, give me examples of office chairs falling off the back of trucks, right? Like, it's going to take, if all you've got is 1,000 cars in the world, or if you're just getting all this data from all these cars, imagine having to have a computer go and look through all of this data that's just raw feed from cars, looking for examples of office chairs falling off the back of trucks, because that's a problem that you're trying to solve. What Tesla can do is they can say, I want office chairs falling off the back of trucks. They can send that out to the fleet, and every car that sees an office chair fall off a truck, it grabs that footage and sends it back to Tesla. So these cars in the field, they're filtering the world. They're using the processors they have in them to filter every single thing they see when they're out driving, looking for examples of things Tesla has requested. They grab that example and they send it back. Mm-hmm. They're not just, they're functioning not as recording devices, but as they're sort of intelligently filtering the world to find things that Tesla has asked for and send them back. And that's really important. That's very different from just having a bunch of recorders out in the world.
Sure. I mean, it's because, I'll just continue on. The thought is Tesla, the neural network is able to pick up certain things very easily, or it's doesn't have a problem. You don't need a ton more data or labeling on the things that they're really good at. You're needing the labeling and the data for the things that you're not good at, because that's what's you're trying to fix, is those cases where you can make a mistake.
The capability is like a bubble that expands, right? And there's this, it doesn't, you don't want to be grabbing data there's no way you can get it yet, right? Mm-hmm. And there's no point in having stuff that's already inside your bubble. You want to be collecting data that's right at the boundary. Like, you can kind of do it, but you can't do it well. Because if you can kind of do it, I can tell the cars in the field, if I ask, this was one that we saw, when we were looking at this, people who hack the cars, they've been seeing Tesla pulling this data for a long time, and they could take apart the triggers to look and see what Tesla was asking for. And there were all these great examples, right? But one of them I really liked was garages, right? And I think this was because someone had a hard time understanding when it was in a garage versus a parking garage versus, had just entered a tunnel or whatever the deal was. And it was interesting looking at some of the stuff that came back, because there are a lot of different kinds of garages in the world, right? And so Tesla was just like, send me pictures of garages, right? And the way that they do that, the cars can kind of recognize a garage. Like, they'll see something, they'll say, well, maybe this is a garage, maybe it's not a garage. If they have no clue if it's a garage or not, there's no point in asking the fleet for it, because you're just going to get random crap back. If the fleet kind of knows what a garage is, but it makes a lot of mistakes, you can ask for all those, and humans can go through those. And if the data is 10% effective or 50% effective, they just throw all the not garage examples away. The others get labeled garage. They go into the training system, right? And what happens is, 2 weeks later, all of a sudden your system is really good at recognizing garages, right? Mm-hmm. And they just go down this list of problems. It can't do this. Ask the fleet, get the data, label it, feed it in. And this is Carpathy's data engine, right? Mm-hmm. They're like, we need this. Ask the fleet. The data comes back, people label it, it goes in, and Operation Vacation for them is the labelers stay in the loop and the system stays in the loop, right? But the engineers, they could go on vacation, and the system keeps getting better because, they look at the next problem, the thing that the car can't do, which they learn from interventions, right? That's why the interventions are really important, because that's human drivers telling you, fix this, fix this, fix this. I had to intervene. They automatically pull that data out. They collate it to look for common phenomena. They figure out, some human being figures out what the common things are. They generate a trigger, send it to the fleet, pull the data, train the network, problem solved, go on to the next one, right?
It's interesting because what you're talking about in terms of, pulling the data, the footage that they need from the cars. It's interesting because my first thing is like, well, how can they pull something that the car doesn't even know what it is? Like, for example, a garage. But I think your example of like, they'll, even if they get recognized, I say 10% of the garages, they'll pull that, but then use that data and labeling, right? The 10% that they were able to accurately put it back into the system. So then the neural net knows better, like how to, look for a garage.
Let me give you a little bit more detail on this, right?
Okay.
So the neural networks, all the camera networks, and they generate this thing called an embedding, which is it's a number that basically tries to describe what the camera is seeing in this very high dimensional space. Maybe, the embeddings are typically 2,000 to 8,000 dimensional vectors or something like that, right? So if you want pictures of garages, what you do is you take pictures of like 100 garages and you run them through the neural network and you look at the embeddings you get out for each one. And the embeddings, they will form a grouping in this high dimensional space, right? In other words, there will be a point in this 1,000 dimensional space, which is the garage point. This is what a garage is, right? The network's uncertain, though. For instance, if I just ask it, tell me what's exactly at this point, I send this point, this embedding out to the network and say, send me stuff that matches this, you're only going to get stuff that exactly matches it, and you're not going to learn anything. What you do instead is you say, send me anything that's within X distance of this. In other words, if you think it kind of might be a garage on all of these dimensions, send me that too. And then a human makes the decision, the labeler does, right? So the system doesn't need to accurately understand what a garage is. It just needs to have a reasonable, kind of a vague idea of what might be a garage. And then you tell it how likely something is to be a garage. If the network thinks it's 90% likely to be a garage, send me all of those. Or you can say, if the network thinks it's 5% likely to send me a garage, all those. So they can try these different confidence figures and they can mine reality for examples that are rich enough, that are things the network wouldn't have caught before, but which it should catch. And so we're going to add those to our labeled data, right? That's sort of how it works. That's how all of these neural networks, they're fundamentally probabilistic. Like when they categorize something, they basically, when it has a lane line, it says, here's a lane line, here's the probabilistic boundary where I think the lane line is. I think it's 90% likely to be here, but there's a 10% chance it's here instead. So what you want to do as you develop the networks is have them have higher confidence in the right answer over time. And so a tool that you always have to work with when you're trying to select data or make decisions about this kind of stuff is you're always getting these probabilities out. You can say, even if you think it's only 5% likely to be a garage, send it to me. Or, if you were doing the office chair falling off the truck, that's a really hard one, right? It might be if you said, tell me, if you think it's 90% probable that it's an office chair falling off a truck, send me that. And you're going to miss a lot of office chairs falling off the trucks because it's never that confident. But if you tell it, 10%, you might get a lot of garbage, but at least you'll get some office chairs falling off a truck. So you have something to work with. And then you have to figure out what that is.
And then you can take that data, the real cases of office chairs, falling off the chair, label them, stick them back into the system.
You can take a bunch of the ones that it thought, maybe this is an office chair falling off a truck, right? And you can stick those in your training pool and you can say, this is definitely not an office chair falling off a truck. And it also gets smarter that way.
That's true. So, and then Tesla pushes out an update and now they're much better at spotting office chairs falling off the truck. And it seems to me as this is happening just constantly, continuously, labeling, catching, using the fleet to pull the footage, the data, to train the networks, it makes more sense in terms of how improvement is going to be compounding, because the ability for the network to be able to train or to pull data that's relevant is growing, because now you have garages, and then you can have bicycles coming out of garages, or you have office chairs falling out of chairs, but you can have different things, a bookcase falling off a chair, or different things. So all of these cases start to grow, but your ability to, and you get better at recognizing, but also the ability to pull more and more data grows because you're recognizing more and more things on the road everywhere. So
And that one of the questions that came up, which is actually a really good question, is like, how do you deal with the march of nines? Because essentially, when we start getting really out in the weeds and we're trying to deal with really rare phenomena, like, how do you deal with that kind of stuff? In order to recognize a chair falling off a truck, you have to know the chair part, and then you have to know the truck part. You have to know I'm on a road. You might have to know it's not sitting on the ground. It's not at the side of the road. I mean, there's all these things you have to understand before you can get to the chair falling off the truck thing. But the thing is, once you have this is a truck and we're in this is a thing that shouldn't be happening. Once you know enough about the way things should be, you can start specifically looking for things that shouldn't be the way that they are. So as the network gets better, your ability to find edge cases rapidly expands. It's true that the edge cases are almost an unlimited universe of edge cases, right? But humans in the real world, they can sense edge cases that they've never seen before. I can be driving, I can not know what a tsunami is or a flood. And if I'm driving down a road and I see a lot of water, I know it's not supposed to be that way and I can stop. The more stuff you know, the easier it is to detect the things that don't fit. And so your lever on dealing with the edge cases actually expands. It doesn't ever converge. Like, you never get to a point where you perfectly understand every edge case. But as the edge cases get harder and harder to detect, if your network is good and you're training it right, the network's ability to detect the edge cases simultaneously gets more and more powerful. So you can continue making progress on making the network better, even as the edge cases get really weird and out there.
Yeah, so this is I think we're getting to kind of like the essence of how Tesla is going to solve, autonomous driving, is this continuous improvement that just compounds over time as their, data and ability to train their network grows. I want to take an example of, let's say, let's look at kind of interventions, how they're used, in combination with maybe pulling data. So let's take an example of, let's say, speed bumps. There's this one footage on Full Self-Driving on Twitter where the Full Self-Driving beta didn't catch the speed bump and just kind of went over very fast. Okay, so let's say in this situation, the driver intervenes, presses the brake or something, and it disengages. So now Tesla knows there's a disengagement. It goes into, and it's pushed out to them, and so they're able to pull that footage of the disengagement, let's say 15, 20 seconds before and after or something. And they pull that and they look at that and they go, oh man, the neural net didn't pick up that this was a speed bump. And so then they can label that. They go, okay, this is a speed bump. But now they don't have enough data to truly, train the neural net that this is a speed bump. So now they push out a request to all their cars saying, hey, look for speed bumps. And then basically the network of cars will bring back images. And going off of what you're saying, depends how much data you want. You could make it more accurate or less accurate, the request. But you bring back, let's say, a bunch of data, and let's say, a certain percent are real speed bumps. You have human labelers, label all these things as speed bumps. In the future with Dojo, you could, let's say structure through motion, you can have them just, like label the speed bump in a structure through motion thing, and all of the frames would be, have that labeled as a speed bump. But for now, let's say they do human labeling for the speed bump on certain frames. And then let's say they're able to get 100 speed bumps back, correctly labeled by human labelers. They put it back into the training system. The neural net gets trained where it reweights, the weightings between certain nodes to basically make the results where they can now, conclude that these are most probably speed bumps. And so now that they push out an update, let's say to these full self-driving beta cars, and now when the full self-driving beta cars go over or approach a speed bump, more likely than not, or the ability for the neural net to pick up the speed bump is greatly improved. So then people are like, whoa, I didn't know, like just a couple of weeks ago, I ran over the speed bump, and now, I'm stopping before the speed bump. I mean, is that generally how the system is kind of working?
Yeah. I mean, that is one mechanism that's going on. You can also do a thing with your interventions, where you push triggers out to the car and say, if there's an intervention, look for these things. And if you see one of them, send it to me. So you can send like the speed bump thing. It's not speed bump, not speed bump. It's there's a dark patch on the road. What's the probability that it's a speed bump? The car thinks. And you tell the control system for the car is like, well, if it's less than 50% probability, don't stop. Or, if it's 90%, stop. Or, it has some kind of threshold. So one thing that you can do right away, you don't even have to retrain the network, is if you're looking at these things and you've told the car, stop if it's 98% chance of a speed bump, because maybe otherwise you're afraid it would be stopping all the time for shadows and random things on the road. And, people drive it for a little while and you find out that the right threshold is really 95%. It's not 98%. So you just push that one number out to the car and all of a sudden the car behavior changes. And it's because you've learned what the right threshold is for taking that action is. So I think a lot of these immediate improvements that we're seeing in the FSD cars, they're probably along those lines because they haven't really had the time. I mean, the data engine, it's a 1 or 2 week cycle for them to push out requests for tags, get the data back, give them to the labelers. The labelers go through, curate the set, label it properly, stick it in, retrain the network, verify that there's no big bad bugs in the network, and then push it back to the cars. It's like a 2 week loop, right? But a thing that you can do right away is you can look and say, well, I had 57 interventions here, and all of them had the speed bump probability between 95 and 98%. We didn't stop. If we had set it to 98, it would be. And then you can look at, you can just bring that number down a little bit. And then you look to see how many places you were slowing down where people press the accelerator instead, right? Because they're telling you, oh, you saw a speed bump and it's not there. And you feed that back into the car also. And it can be, it's probably more than just speed bump versus not speed bump, right? They probably have more categories of stuff going in there. So you can slice that problem a little bit more finely too, because there's speed bumps, it's a yellow stripe on the road. And there are other speed bumps where it's a shadow, and you might have different categories for those.
Got it. So, it's interesting. So, you're saying that these certain variables or settings that, for example, the percent, let's say 95%, or the threshold that it requires for them to, let's say, stop at a speed bump, that stuff you think can be pushed out without a big firmware update, you're saying, basically through push type of software setting updates, right?
So what I understand has been seen from people who have watched these things go back and forth between Tesla and the cars is that neural network weight updates, they only happen with relatively big pushes. Now, so the packages that get seen, the neural networks are big. They're large files and they're highly interdependent with a bunch of other stuff. And the packages that get pushed out by the car that update the neural networks, as far as I know, they only happen with a pretty big push, which is the kind where, the car has to go to sleep and wake back up and it takes 30 minutes to install it or whatever the deal is. There could be exceptions to that. Like it's possible some of the neural networks, there's a bunch of neural networks in the thing. And it could be that you have a small neural network, say the windshield wiper network. This is something that they struggled with for a really long time. And for like a year, the neural network, it kept getting bigger and smaller, and it was combined with this and that, and it just moved all over the place as they were trying to figure out like how to get the windshield wipers to accurately detect rain, right? But it's a relatively low risk neural network. Like you could, and there were times where it was pretty small. So it's conceivable, although as far as I know, nobody ever saw this happen, that Tesla could have just pushed out a new neural, windshield wiper network if they really wanted to try something. Nobody saw that happen, but it's not beyond the realm of possibility. On the other hand, there are these smaller sort of hyperparameter files, right? And it looks like they do get updated, right? So you could have a file that's got a bunch of these percentages, like slow down if the curve is tighter than this, or stop if with this probability if you see this. And the windshield wiper thing, it was producing a rain probability. Like it had these, it changed a bunch of times. So for a while, it had these different categories of rain, like, is it drizzling? Is it, or whatever? And it would give you a probability in each of those categories. And then the software that would turn on the windshield wipers, it would look at those probabilities and make a decision. And you could imagine that those are numbers that you could move around, right?
Mm-hmm. Definitely. This is great. I think it's definitely helping me to understand. I think it's going to help others as well. I want to ask some questions on this whole idea of the perception engine for autopilot or full self-driving versus like the planning kind of, section. So, from my understanding, you have this perception type of system where you're trying to understand the world, right? And what objects are going around, moving around, basically interpreting what's happening. But then there's another type of set of challenges, which is how do you navigate through that world? What decisions do you make? How fast do you go? When do you turn? How do you turn, etc.? And it seems like what Tesla has this stuff in a separate type of system of planning, a system where it's just determining how to plan. And some people have asked me on Twitter, is this planning system mostly like hand coded, things, and is there use of neural nets in terms of actually making the planning more automated, or the improvements to the planning more automated? Or do you foresee kind of this planning system still being kind of hand code driven, into the future?
Yeah, so people talk about these systems as like planning, perception, and action, right? And got these three big categories of stuff. And the big challenge has been having accurate perception up until now. So that's the there are things in planning which are really amenable to a neural network doing them, and there are other things that are less amenable. And all of these systems have, I call them a harness that it runs in. You have this. All of them have handwritten code that looks for really stupid stuff that's almost certainly a mistake, and it prevents bad outcomes by looking at that. The harness is mainly there to catch bugs, because neural networks can have bugs too, right? I mean, you can have something which is just like this really weird output that you get. It's very rare, but it does happen. And building the harness is relatively straightforward. You kind of do it once and you don't have to do it again. And everybody who builds robotic systems in the real world, they have a harness around this thing that looks for, and you can look at, there are lots of different ways you can examine this, the output of these neural networks and these planning systems to decide if it makes sense or not. And the harness will intervene and prevent that. Now, it used to be like, especially on AP1 and early AP2, you would see the harness kick in all the time. Like you could see all these hard thresholds, or like it would be doing a thing and then the harness would kick in, right? Like one of them, AP2 for a really long time, it had a harness around how tight you could turn on a freeway, right? Because one of the failure modes they had is the wheel deciding to turn too tight for how fast you were going on the road, right? And so for a long time, the car's main failure mode on highways was slowly drifting out of its lane. You'd be driving, maybe the speed limit's 65, but the traffic's going 75, so you're going 75, and you come on a relatively tight turn, and you'd see the car just slowly drift out of the lane. You're like, what is going on with that? I mean, you could look at the display, and the display lines, it clearly knew where the lane was because you could see it drifting around the lane. Why wouldn't it stay in the lane? Well, the reason is they had a hard setting that said, at this speed, you cannot turn the wheel harder than this, right? Because that was a safety harness. And the harness kicking in is what prevented the car from getting in the lane, because you just happened to be on a road where how fast you were going too fast for how fast the harness would let you turn in that kind of situation. And for a while they needed that because the curve prediction accuracy wasn't good enough that you could avoid occasional really bad situations, right? Like, there's this hill cresting problem they used to have where for a long time, the way that it understood where it was on the road was it looked for lane lines. Like in the beginning, lane lines were really important. They're very unimportant now, especially with FSD. Just human beings treat a lane line as if it's just suggestion, because you can cross, if it makes sense, you cross a lane line, right? If it's safer to do that or quicker, you just cross a lane line. But autopilot for a long time, lane lines were God. They were like concrete boundaries, and like it wouldn't cross it wouldn't cross one of those unless the harness kicked in and said that it had to, right? And that was the one situation that it would do. But so you had this hill cresting problem where like you're driving down a road and the road's kind of going up and down, right? And it's got a little wobble back and forth to it. And occasionally you get a thing where you're kind of on a curve, and as you're cresting a curve, there's the car can't see the lane lines over the curve, so it doesn't know where the lane goes, right? Now, if you're on a completely dead straight road and it crests, the car would guess, oh, it's probably straight on the other side, right? But if you're curving, when it gets to the top, it's like, because a lot of times the curve changes right after you crest the hill or goes straight. Sometimes the car would freak out at the crest, right? Like because the lane line just disappears and it's got no horizon for the road or whatnot. And then, just as you're cresting the road, it can kind of see some marks on the far side that are giving an idea that the lane goes this way, the lane goes that way. And suddenly it would want to turn the wheel right at the crest of the hill. this was a really common failure mode. And if you drove on those kinds of roads very often, you would see it all the time. You could predict it as a driver. You're just like, oh, it's going to happen right here. You'd be coming up and the wheel would suddenly jerk. And the harness was a way of making sure that those jerks were never bad enough that they would cause an accident, right? So you have these harnesses in there. So nothing is completely without hand code, right? There are harnesses, there are going to be these safety harnesses all throughout the system that look for stuff. Perception didn't used to all be neural networks. It seems like perception is almost all neural networks now. The camera networks in FSD, they now have radar getting fed into them, which they didn't used to. It used to be that neural networks would process the camera, had a separate neural network for radar someplace, and then there were some other networks that would combine that and some heuristic code that would combine it. But now they're starting to bring more and more of the sensors together at an earlier phase of the thing. And those networks, they're, as the system gets developed, they extend farther and farther up into in perception. I would guess at this point, there's a lot of stuff I can't see. The stuff I can see is neural networks. Like the stuff that I get access to is just, that's what we go looking for. That's what the other guys give me, and that's what I get to process. So I can look at it and see what's in the neural networks, but I have to guess about what's not in the neural networks, which I do by observing how the system behaves and, just sort of common sense and that kind of stuff. The neural networks, they're accumulating more planning-like features in them, but planning isn't entirely neural network. And to some extent, like, we're not in any reasonable time going to get to a point where you stick the Google map in the neural network and then the neural network decides, how you get. There's going to be heuristic stuff for route planning and all that kind of stuff. And it has to interface to some level of the planning module. What lane do I need to be in when I cross this intersection? Depends a lot on where you want to go. And there's going to be a heuristic mapping module that's going to decide that kind of stuff. And it's going to be part of that equation for a really long time. But the whole decision about, like, how fast do I move over to the left lane so that I can take this left, or is that not safe? And should I just go through the light and take the next left and come back? Those trade-off kinds of decisions are eventually going to be almost all in the neural network, but they're not now. So planning, there's a decent amount of very neural networky stuff in there that I think is already being done by the network. There's a huge amount of stuff that's not neural network now, and probably isn't going to be in any reasonable amount of time. And that boundary is constantly shifting. As a neural network can do and more of it, they hand more of it to the neural network. And then what they had before becomes a bigger part of the safety harness, right? It becomes a stop back measure to make sure that the neural network is behaving itself. Does that answer your question?
Yeah, that makes sense. So in your opinion, the perception, the problem is the big problem. I mean, is the planning, it would be more secondary, the challenges that faces over time?
So all of these systems have aspects which are either better or poorly suited to heuristic code versus handwritten code versus what neural networks do. And it's a moving target, right? The heuristic stuff has been around for a long time, and robotics is a mature field. Like, there are a lot of well understood techniques for dealing with these things at heuristics, and we have a pretty good understanding of the bound of what those things can do. So a good thing to start out with is you build it that way. And then as the neural network's abilities in that space overcome the heuristics, then you hand that over to the neural network. And then once again, the heuristic becomes part of the safety harness for the neural network at that point.
I hope that conversation was helpful. If it was, please consider liking the video to help spread the word and subscribing to my channel to keep updated on new videos. I'd actually interviewed James Douma over a week ago for 2 hours, but after recording, I found out that the first hour didn't save because of lack of storage on my computer. So I asked James if he would be willing to talk again, and he graciously offered his time. So the excerpt you saw was from my second interview from him. The full interview is over 3 hours, and we cover a lot more topics, such as how much Tesla can charge for full self-driving in the future, who's the competition, and a whole host of other topics. I'll link to the full video in the video description below. Also, later this week, I will share an excerpt from my first interview with James, and it's about how Tesla can leverage their AI experience to enter new markets besides autonomous driving. If you're on Twitter, I'm active there at HeyDave7. Also, if you listen to podcasts, all my YouTube videos are on an audio podcast. Just go to your podcast player and search for Dave Lee on Investing. I hope to see you in my next video. Thanks.